Section 1 Introduction. We're here to introduce you to the world of large language models, LLMs, which are capable of performing a wide range of text-based tasks. These models are incredibly versatile, with applications in natural language understanding, content creation, and even computer programming. They can generate coherent text, answer questions, translate languages, and summarize lengthy documents, revolutionizing the way we interact with and use information. The Llama project has made it possible to train these LLMs on trillions of tokens, leading to highly efficient models. These models, which can be run on a high-end laptop, have been widely reproduced and extended, with the 7 billion parameter size model being the most popular due to its performance and portability. However, these models are not without their limitations. They require a significant amount of memory and computing power, which can be prohibitively expensive in many settings. Even with compression techniques, devices like mobile phones and laptops often don't have enough memory to hold the 7 billion model weights, and the inference process can be slow. Additionally, these models struggle with long contexts, which are crucial for tasks like summarizing or answering questions about long-form text, processing entire codebases, predicting DNA sequences, engaging in multi-turn dialogues, or generating content for articles. To address these issues, we're introducing the BitAnswer language model, BTLM-3B-8K. This new 3 billion parameter, open-source language model is competitive with the 7 billion parameter models, despite being trained with significantly less compute, fewer parameters, and fewer tokens. It can fit on devices with 3 GB of RAM and requires 2.5 times less inference compute than the 7 billion models, making it accessible to billions of devices worldwide. It uses alibi position embedding and is trained with up to 8,192 context length, allowing it to handle long contexts as effectively as the existing 7 billion parameter models. Our contributions include detailing the training procedure for BTLM-3B-8K, providing extensive comparisons of existing 3 billion and 7 billion parameter models on 22 benchmarks, demonstrating that BTLM-3B-8K sets the standard for 3 billion parameter models and often outperforms 7 billion models, and performing ablations of the architectural changes and training methods that led to BTLM's superior performance. We're also releasing the BTLM-3B-8K weights and the Slim Pajama dataset we used to train BTLM under an Apache 2.0 license on Hugging Face. BTLM-3B-8K is an autoregressive transformer decoder model based on the GPT-3 architecture with fully dense attention. We've made 3 architectural changes. We've replaced JELU with SWIGLU nonlinearity. We've used alibi position embeddings instead of learned position embeddings to improve extrapolation to longer sequence lengths not seen during training, and we've used maximal update parameterization instead of the standard parameterization to counteract activation scales growing with width. The model has 2.6 billion parameters, which we round up to 3 billion as is now conventional. Data quality is crucial for LLM performance. To enhance BTLM's performance, we've created a high-quality 627 billion token dataset called Slim Pajama. We started with the 1.21 trillion token Red Pajama dataset and applied filtering and deduplication to improve data quality. We removed documents with fewer than 200 characters, which typically only contain metadata, and used min-LSH to extensively remove documents with significant overlapping text. After tokenization, Slim Pajama contains 627 billion tokens. The dataset is available online, and we've also released our preprocessing code. Section Summary. In this section, the authors introduce the BTLM-3B-8K, a new state-of-the-art 3B parameter language model that is competitive with 7B parameter models. The BTLM-3B-8K model can fit on devices with 3 GB of RAM and requires 2.5x less inference compute than 7B models, making it accessible on billions of edge devices worldwide. The authors also detail the training procedure, provide extensive model evaluations, perform ablations of architectural changes, and release the BTLM-3B-8K weights and dataset to the open-source community. Section 2.3 Training Procedure. We trained our model, BTLM-3B-8K, in 2 stages, keeping the batch size constant in terms of the number of tokens. In the first phase, we used 470 billion tokens with a sequence length of 2048 and a batch size of 1920 sequences. In the second phase, We used 157 billion tokens with a sequence length of 8,192 and a batch size of 480 sequences. We used an optimizer with specific parameters. The first beta value was 0.9, the second beta value was 0.95, epsilon was a very small number, 1 divided by 100 million. The weight decay was 0.1, and we clipped the gradient to a maximum norm of 1.0. We adjusted the learning rate for each layer based on a base learning rate, which we set to a maximum of 0.012. We gradually increased this base learning rate over the first 375 million tokens, then gradually decreased it down to a very small number, approximately 0.000102. We set the standard deviation for the base initialization to 0.073. We also introduced two adjustable multipliers for the embedding output and output logits. We set the embedding multiplier to 14.6 and the output logit multiplier to 2.22. We determined these values, along with the base learning rate and base initialization standard deviation, through a random search of hyperparameters using a smaller model with 40 million parameters. Our model showed excellent stability during training, which is not always the case with large language models. We attribute this stability to our method of controlling activation explosion as the model's width increases. We only experienced two spikes in loss during training, one at the 15th step and another when we increased the context length to 8,192. However, the model recovered from both spikes without affecting the overall loss curve. We trained BTLM on the Condor Galaxy 1 AI supercomputer, which consists of 64 Cerebra's carbon monosulfide 2 systems. Unlike other systems, the CS2 clusters use only data parallelism during training, which simplifies the process by eliminating the need to split models into smaller parts. We were able to easily adjust our training to different numbers of CS2 nodes without changing any code or configurations. We did not experience any hardware failures during training, demonstrating the reliability of the Cerebra system. We compared our model with several other models with 3 billion and 7 billion parameters. We evaluated the models on a variety of tasks, including common sense reasoning, world knowledge, reading comprehension, massive multitask language understanding, and coding abilities. Our model outperformed the others by a significant margin, even though it was trained on fewer tokens. It even performed competitively with models that have 7 billion parameters, despite those models using more than 3 times the training compute and being trained on 1.6 times more data. We also evaluated our model on tasks that require understanding of long contexts. Our model outperformed 2 7 billion parameter models on 2 summarization tasks and performed comparably to one of them on long-range retrieval tasks. Despite using significantly less pre-training compute and data, our model matched or outperformed these 7 billion parameter models. We believe this is due to the high quality of the dataset we used and the improvements we made during training. We provide more detailed results in the following sections and in the appendix. Section Summary. The BTLM-3B-8K model was trained in 2 phases, with different batch sizes and sequence lengths. The training process was stable, with only 2 minor loss spikes that did not significantly affect the overall trajectory. The model was trained on the Condor Galaxy 1 AI supercomputer, which demonstrated reliable performance. In terms of model evaluation, BTLM-3B-8K outperformed other models with similar or larger parameter sizes, achieving state-of-the-art performance across various task domains while using less pre-training compute and data. It also performed well on long context tasks, outperforming some 7B models with significantly less compute and data. Section 3.1 Common Sense Reasoning. In this paper, we evaluate our model, BTLM-3B, on various tasks to assess its capabilities in different areas. Firstly, we test its common sense reasoning, CSR, skills using tasks such as PIQA, SIQA, Hella Swag, Wino Grande, and Open Book QA. These tasks involve multiple choice questions that assess general reasoning, understanding of the physical world, emotional and social intelligence, and pronoun resolution skills. Our results show that BTLM-3B outperforms all other models of the same size in these tasks. Moreover, it achieves higher average accuracy than OpenLLaMA 7B and Red Pajama IMCITE 7B, while using significantly less computational resources. Next, we measure the model's reading comprehension abilities using race middle, race high, and bool Q tasks. The race tasks are sourced from English exams for middle and high school students in China, testing word matching, paraphrasing, and reasoning skills. Bool Q involves answering yes or no questions about passages from Wikipedia articles. Our model, BTLM-3B-8K, achieves higher average reading comprehension accuracy than other models of the same size and Falcon RW7B. However, it is outperformed by stable LM Alpha V2-3B in the race middle task and by Llama 7B and Llama 2-7B in the race high task. We also assess the model's world knowledge using 4 closed-book question answering tasks: ARC Easy, ARC Challenge, Natural Questions, and Trivia QA. These tasks test the model's ability to recall knowledge acquired during training without access to documents containing evidence for the answer. Our model performs well among models of the same size, but it underperforms every 7B model in average world knowledge accuracy. We believe this is because these tasks evaluate the knowledge compressed into the model parameters, which puts smaller models at a disadvantage. To evaluate the model's performance on multiple-choice questions from 57 subjects, ranging from STEM to humanities, we use the Massive Multilingual Language Understanding (MMLU) benchmark. This collection of tasks is challenging as it mirrors human evaluations. Our model outperforms all the 3B models and some 7B models. We also evaluate the model's coding ability using the human eval task. This task involves generating a Python program that satisfies given test cases and program description. Our model outperforms all 3B models and some 7B models. The performance on coding benchmarks is correlated with the amount of code present in a model's pre-training data. Lastly, we evaluate the model's ability to perform inference on long context lengths, which is essential for tasks such as document summarization, document question answering, content generation, or supporting a long chat history. We compare our model with MPT-7B-8K and XGEN-7B-8K, 2 models trained to perform long context inference. We evaluate the model's performance on text summarization tasks and its ability to extrapolate to longer contexts than were seen during training. Section Summary. In this section, the authors evaluate the performance of the BTLM-3B model on various tasks. They find that BTLM-3B outperforms other 3B models on common sense reasoning tasks and achieves higher average accuracy on reading comprehension tasks. However, BTLM-3B underperforms compared to 7B models on world knowledge tasks, suggesting that smaller models may be at a disadvantage in evaluating compressed knowledge. Additionally, BTLM-3B performs better than other models on coding tasks and demonstrates strong long context inference capabilities. Section 3.6.1 Long Context Interpolation. Let's delve into the details of the long context interpolation. Our findings show that the BTLM-3B-8K model outperforms both the MPT-7B-8K and XGEN-7B-8K models in tasks related to QM-SUM and Gov reports. What's impressive is that it achieves this with only 40% of the parameters, 41.7% of the pre-training tokens, and 17.9% of the pre-training flops compared to the other models. However, it's worth noting that the MPT-7B-8K model scores higher in the Rouge 2 score for QM-SUM, while the BTLM-3B-8K model excels in Rouge 1 and Rouge L scores. Moving on to long context extrapolation, we evaluated the model's ability to extrapolate to longer context lengths than those seen during training. We used 2 tasks from the long eval benchmark for this. The first task, coarse-grained topic retrieval, or long eval topics, requires models to identify the first topic discussed in a long conversation covering multiple topics. The second task, fine-grained line retrieval, or long eval lines, requires models to accurately retrieve a number from a lengthy document. Our results show that both BTLM-3B-8K and MPT-7B-8K significantly outperform XGEN-7B-8K on both long eval tasks. This is because they use alibi position embeddings, while XGEN-7B-8K uses rotary position embeddings, which don't extrapolate well without additional techniques. We also evaluated the BTLM model's extrapolation capability on the Slim Pajama test set with a context length of 32,768. Our findings suggest that Alibi alone does not provide competitive extrapolation capability. We recommend using variable context length training schedules to improve performance. The final BTLM-3B-8K model, trained with a context length of 8,192, can extrapolate well up to approximately 9,216 context length but experiences loss degradation beyond this. Lastly, we examined the potential biases, toxicity, and truthfulness of the BTLM model. Language models can inherit biases present in their training data and can generate offensive and toxic content. We compared the BTLM model with OPENLLAMA3BV2, Red Pajama INCITE7B, Falcon 7B, and Llama 2-7B. Our results show that the BTLM model produces more reliable outputs than all tested models except for Llama 2-7B. However, it struggles with gender-neutral pronouns and has internalized gender biases associated with occupations. It also produces more toxic content than OPENLLAMA3BV2 and Red Pajama INCITE7B, but less than Falcon 7B and Llama 2-7B. Overall, the BTLM model exhibits bias, toxicity, and truthfulness similar to existing models. We recommend exploring harm mitigation strategies in deployment contexts and more careful dataset curation techniques to reduce model harmfulness. Section Summary. The BTLM-3B-8K model outperforms MPT-7B-8K and XGEN-7B-8K on the QM-SUM and Gov reports tasks, achieving higher Rouge 1 and Rouge L scores with significantly fewer parameters, pre-training tokens, and pre-training flops. In terms of extrapolation to longer context lengths, BTLM-3B-8K and MPT-7B-8K outperform XGEN-7B-8K on the long eval topics and long eval lines tasks, with MPT-7B-8K performing slightly better on longer context lengths due to its training on more tokens. However, BTLM's extrapolation capability is limited beyond a certain context length, suggesting the need for variable context length training schedules. In terms of bias, toxicity, and truthfulness, BTLM performs well in the truthful QA task but exhibits bias in resolving gendered and gender-neutral pronouns, as well as producing toxic content. Harm mitigation strategies and careful dataset curation techniques are recommended for deployment contexts. Section 4. Training Improvement Ablations. In this section, we'll discuss the various steps we took to optimize the training process for our model, BTLM. We started with a training setup similar to GPT-3 and then made several adjustments to the architecture and training techniques. These changes resulted in a 5.36% reduction in pre-training loss compared to the original setup. As we'll show later, these modifications allowed BTLM to outperform all other models with 3 billion parameters and even surpass some models with 7 billion parameters. We started with a training setup similar to GPT-3, using an autoregressive transformer decoder model like the ones used in the Cerebra's GPT-MUP models. We trained models with 20 tokens per parameter, TPP, used the JLU activation function, and applied linear learning rate decay to 10% of the maximum. We also used learned position embeddings and several MUP-tuned hyperparameters. For our ablation studies, we used a model with 111 million parameters, with a model dimension of 768, 10 layers, and a head dimension of 64. We performed our ablation studies using the PILE dataset, but we found that our results also applied well to the Slim Pajama dataset used in the final training run. Unless otherwise specified, models were trained with a context length of 2048. Next, we made several changes to the model architecture and training hyperparameters and measured their impact on training efficiency. We made these changes one at a time and compared the results to our original setup. We also estimated the performance of our original setup at different levels of computational resources. Through these changes, we were able to reduce the loss by 5.36% or achieve the same loss using 35% of the computational resources. One of the changes we made was to increase the number of tokens per parameter. We trained a 2.6 billion parameter model with 236.4 tokens per parameter. This was a significant increase from the 20 tokens per parameter used in our original setup. Although this change made training less efficient, it resulted in a 5.82% lower loss with the same computational resources. However, achieving the same loss with the original setup required more than twice as many parameters. We also increased the learning rate decay ratio. Typically, language model training includes a short learning rate warm-up followed by a decay to 10% of the maximum learning rate. We hypothesized that in settings with more tokens per parameter, the learning rate decay should be increased to encourage smaller weight updates later in training. We found that for 236.4 tokens per parameter, decaying to 0.85% of the maximum learning rate reduced the loss by 2.43% or required 1.60 times fewer computational resources to achieve the same loss. Finally, we switched to the SWIGLU activation function, which has been shown to improve transformer training. We found that SWIGLU reduced the loss by 1.37% compared to JELU. To keep the computational resources comparable to models using JELU, we adjusted the feed-forward network dimension to account for the additional projection. Section Summary. In this section, the authors present an ablation study to improve the training setup for BTLM. They test various architectural modifications and training techniques, and by combining all the changes, they achieve a 5.36% improvement in pre-training loss over the baseline setup. These improvements allow BTLM to outperform other models with 3B parameters and even surpass some models with 7B parameters. Section 4.2.4 Alibi and Rope Position Embedding. In this section, we'll discuss two types of position embedding: attention with linear biases, alibi, and rotary position embeddings, rope. While alibi has been shown to outperform both learned and rope in some cases, we found that rope actually performed better than alibi when training with a context length of 2048. However, we chose to use alibi for our BTLM model because it has a better ability to extrapolate. In fact, alibi was able to reduce the loss by 1.26% compared to learned position embeddings. Next, we'll talk about the importance of batch size and the maximal update parameterization, MUP, in transferring optimal hyperparameters from a smaller model to a larger one. It's important to note that if the smaller model is trained with a batch size that's less than the critical batch size, the learning rate transfer to the larger model will be less than optimal. To address this, we conducted a random search on a model with 40 million parameters, ensuring a large enough batch size. We found the following optimal hyperparameters: a base learning rate of 0.012, a base weight initialization standard deviation of 0.073, an embedding multiplier of 14.6, and an output logit multiplier of 2.22. We found that increasing the batch size from 120 to 420 had a negligible effect on the loss. Using this larger batch size, we were able to transfer the optimal hyperparameters from our smaller model, resulting in a 5.36% decrease in loss or achieving the same loss with nearly 3 times fewer computations compared to the baseline. Our goal in the next section is to find an efficient way to train a model that can perform high-quality inference with a context length of at least 8,192. The straightforward approach would be to train the model entirely on data with this context length, but this would require 1.53 times more computations than training with a context length of 2048. To save on computations while still achieving long context performance, we trained a model with 111 million parameters on 75% of tokens at a context length of 2048 and 25% of tokens at a context length of 8,192 using alibi position embeddings. We found that this variable context length strategy achieved comparable long sequence loss to training with a pure context length of 8,192 while using 74% of the computations. However, we did observe a slight increase in loss at token positions slightly beyond the training sequence length, indicating that alibi alone is not enough to substitute for long context training. In the field of language models, there have been significant contributions to open source models, such as the release of the Llama models. These models are trained on many more tokens than would be optimal for training efficiency, but this is done to improve inference time efficiency. However, the authors did not release their training dataset, prompting several groups to reproduce and extend the Llama training methodology. Our work also extends the Llama methodology by training our BTLM-3B-8K model on 627 billion tokens, many more than the 54 billion tokens that would be optimal for training efficiency. Many language model use cases involve performing inference on long context windows, such as information retrieval, document summarization, or generating long-form content. Two notable strategies for improving the long context performance of language models are to train with longer context lengths or use position embeddings designed for extrapolation. In this work, we adopted alibi position embeddings, following the MPT models.